Hello everyone and welcome to today's webinar, which is brought to you by Picarro in partnership with Eosense, the University of Leeds and ASO Network, and is titled Evaluating the Benefits of Plasma-Treated Organic Fertilizers with Soil Gas Flux Measurements. A big thank you to everyone involved in making this event possible. Before we start, I'm going to explain a little bit about the format for today's webinar and how you can get the most out of your experience. So today's webinar will consist of a presentation and audience Q&A, and we have three fantastic speakers joining us. Getting us started in just a moment will be Dr. Karen Drury from Picarro. Dr. Drury drives product innovation and strategic growth. She's a PhD in molecular biology and biochemistry. She blends scientific expertise with business acumen to lead a team of product managers. Throughout her career, which has spanned over 2 decades, Karen has established herself as a dynamic business leader and technical expert in the field of scientific instrumentation. She's going to get started in a couple of moments and then hand things over to Dr. Nicholas Nickerson from Eosense. Dr. Nickerson combines his expertise in ecological research, numerical modeling, and sensor design to advance greenhouse gas measurement technologies. He has a PhD in earth sciences from Dalhousie University and over 15 peer-reviewed publications. Nick remains highly engaged with the research community. And finish things up will be Dr. Isabel Lloyd. Dr. Lloyd is a soil scientist and graduated from the University of Leeds in 2024 with a PhD in geography. Her research focused on the fluxes of greenhouse gases from agricultural soils under different farming methods. The aim was to improve knowledge of these emissions and provide insights to help reduce the agricultural sector's environmental impact while maintaining food security. A big welcome to the three of you today. Just before we get started, a few points about how to enhance your experience today. Firstly, you can ask questions at any time. You'll find the Q&A box on the right-hand side of your screen, so please send those in as and when they come to mind. The event is being recorded. We'll be sharing the on-demand link with you within the next 24 hours. So if you enjoy what you see, or you have a colleague or peer who might benefit from seeing the content, then please consider sharing with them internally when you get that email. You'll find several handouts on the left-hand side of your screen that you can download at any stage today. So do please take a look at those and download them before we finish up. And finally, if you experience any technical issues, then they are normally resolved by refreshing your browser. If this doesn't work, send our team a message using the Q&A box. Our backend team will get you back up and running as quickly as possible. Okay, right, let's get things started. Karen, over to you.
Hi everyone and welcome. Big thank you, Danny, for organizing this webinar and introducing me. I'm Karen Drury from Picarro and I'm excited to be here today. So let's get started. Now let me quickly introduce Picarro. We are a leading provider of solutions for measuring greenhouse gases, trace gases, and stable isotope. Our technology is used in areas like soil flux, industrial monitoring, air quality, and energy. Picarro owns over 65 patents, many of which are exclusively licensed from Stanford University. We are ISO certified company, and our headquarters, including our R&D and manufacturing, are based in Santa Clara, California. We're a growing team of over 300 people, including more than 60 PhDs. And our instruments are used in over 95 countries around the world. So with that background on Picarro, let me now give you a closer look at the types of analyzer we specialize in. At Picarro, we design and manufacture advanced analyzer for measuring a wide range of gases and isotopes. This includes greenhouse gases, trace gases, VOCs, and even water and carbon isotope ratios. Our instruments are built to deliver high accuracy, real-time data, which is critical for application across fields like soil flux measurement, environmental monitoring, and energy production. At the heart of Picarro technology is our CRDS, or cavity ring down spectroscopy. These methods allow for highly sensitive, precise measurement with minimal interference. When it comes to our instruments, we really focus on 5 key attributes that we like to call the 5 S's of Picarro. First, there is sensitivity. Our instruments are designed to provide highly accurate measurement, even at very low detection limit. Then we have stability, which means you can count on constant, reliable results, even in the most challenging environments. We also emphasize selectivity, so our instrument can measure specific gases without interference from others, ensuring the data you get is exactly what you need. Speed is another important factor. We provide a real-time data collection, allowing you to get quick insight as you go. And lastly, there is simplicity. Our analyzers are easy to use and require minimal maintenance, so you can focus on your work without worrying about the technology. Those 5 qualities are what makes our instruments stand out and help you achieve the best results. Now that we've covered our technology and its benefit, let's dive into one specific application, soil flux measurement. This is an area where Picarro really shines, and Izzy will be going into more details on this in her presentation. For soil flux measurement, we offer the G2508 greenhouse gas concentration analyzer. It's a powerful tool that can measure N2O, CH4, CO2, NH3, and water all at once in a single device. Whether you're working with open or closed system, it integrates smoothly with most chamber setups. This makes it perfect for studying soil emission and understanding the environmental impact of different gases. Izzy will take you through this application in more depth, but the 2508 is a great example on how our technology support important environmental research. Before we wrap up, I'm really excited to share Picarro's newest addition to our product lineup, the Sage gas autosampler. This new autosampler is all about efficiency, designed for high throughput gas sample analysis. It operates automatically, saving you time and making your workflow smoother. With a 150 position vial rack for 12 milliliter headspace vial, it really boosts sample throughput. And the best part, it integrates seamlessly with Picarro analyzers, making it the entire process much more efficient. The software is super user-friendly, so analyzing data and exporting results is a breeze. It's perfect fit for high throughput application where you need both accuracy and speed. This is a powerful tool for anyone needing a precise gas and isotope measurement in a high volume environment. Now I'll hand it over to Nick Nickerson, who will introduce the Eosense technology.
Okay, thanks, Karen, for introducing me. And I'm just going to take everybody through a quick overview of Eosense, who we are and what we do before we get on to Izzy's presentation. So Eosense designs and builds greenhouse gas measurement hardware and software for researchers. We were founded in 2009, and we're now a team of actually 15 starting today, people based in Dartmouth, Nova Scotia in Canada. And our products have been used by researchers globally at this point. What Izzy will be talking about and kind of what we do as our bread and butter, as it were, is automated chamber systems. So these are systems that are designed for long-term continuous measurements of gases like CO2, methane, nitrous oxide, and other gas species. We've spent the time to fully integrate these systems with the Picarro analyzers. So that's, for example, the analyzer Karen was talking about, the G2508, but also a variety of other Picarro gas and isotopic analyzers. We provide a multiplexer for these chambers that can allow users to connect up to 16 chambers to those Picarro analyzers, which you can see in the top kind of right corner of this slide here. And we have the most flexible chamber options, I think, of any company producing chambers. So we have transparent and opaque options of both of our chambers. We have various footprints. So we have a large chamber, which Izzy will be talking about, and we've got a smaller chamber. And we also have what I'll show you next, which are different height adjustments for those chambers. So the base extensions we have are specifically to help users measure things like photosynthesis, net ecosystem exchange, but specifically to put plants and vegetation within the chamber footprint. So we have two options for that. The first one is a 30 centimeter stacking base, and with the large chamber that increases the total chamber height to 75 centimeters. Or we've got the 70 centimeter stacking bases, which will increase the total chamber height to about 115 centimeters. So the idea with these is to try to include vegetation and really like work on those problems where you need the vegetation as part of your flux measurements to understand what's going on. In addition to that, we also produce software that helps researchers run these systems. So we have our EOSLink family of software, which is what runs on the Picarro analyzers and allows users to control and customize their measurement schedules, to synchronize chamber closure time and the analyzer timestamp, and just to make it easy to pull together the data time series from the Picarro analyzers and the time series from our Eosense instruments. And in addition to that, we also have our EOSAnalyze family of software, which will allow you to do the flux calculations in an automated kind of way. So we pull in the data from the analyzers, we pull in the data from the chambers, we combine those data sets together for the user, and the software will perform linear and exponential curve fitting. It'll allow you to visualize that data so that you can QC it, change your dead bands, exclude outlier points, and then export it as a CSV or similar file for your additional analysis. So now I'm going to hand it over to Izzy so she can take you through some actually applied research using the Picarro and Eosense systems.
Brilliant, thanks Nick, and a big thanks to Eosense and Picarro for inviting me to speak at this webinar today. Yep, my name is Izzy, I am a soil scientist based in the UK, and today I'm going to share the results of an experiment which was conducted as part of my PhD at the University of Leeds a couple of years ago. The study focused on measuring greenhouse gas fluxes from soils fertilised with treated and non-treated pig slurry, and you can see there a photograph of the experiment where we had our setup of Eosense chambers. I'd also quickly like to highlight that this study has been published in Nutrient Cycling in Agroecosystems, and so if you would like to read about the study and the findings in any more detail or see any more of the plots, then you can do so following the webinar, as you will have access to a copy of the paper. So first of all, I'll give a little bit of background about greenhouse gas emissions from fertilizer use. And here we're talking in the context of the UK, as that's where the study was conducted. So you can see here in the chart on the right-hand side, greenhouse gas emissions and the contribution of agriculture, which is the blue bar, and any other sources, which is the orange bar, to these greenhouse gas emissions. And you can see that agriculture makes a significant contribution compared to these other sources, particularly for methane and even more so for nitrous oxide. In agriculture, these nitrous oxide emissions mainly stem from fertilizer application to land. In the field, excessive applications of fertilizers and therefore the nitrogen that they contain mean that this excess nitrogen is available in the soil for nitrification and denitrification, which results in nitrous oxide emissions to the atmosphere. In addition, these methane emissions stem from the use but also the storage of organic wastes, which are then used as fertilizers. So when organic wastes such as manures, so cattle manure or pig slurry for example, when these products are stored, they facilitate the conditions for methanogenesis, which is the process that produces methane. So examples of these conditions are a source of carbon, and very specific temperature ranges which activate those microbes. And so during storage, these conditions are perfect for that methane production. So it's produced in the storage, absorbed into the organic products, the manure or the slurry, dissolved into the waste. And then when the slurry is applied to the land as a fertilizer, that methane is released to the atmosphere. So these high emissions are therefore a problem, particularly when we consider that graph on the right-hand side, and especially if we are to mitigate climate change and global warming and try to reduce the effects of these global problems. We therefore need to try and find ways that we can reduce these emissions from fertilizer storage and spreading. You can see there a few examples of these mitigation methods, the first being the plasma induction process, which I'll explain in a little bit more detail in a second. But we can also use methods such as split application, which is when fertilizers are applied at different growth stages to better match the nutrients that a crop will need when it needs it the most at certain stages in its life. We can also use a combination of organic and inorganic fertilizers, which means that nutrients are supplied in different forms and released to the crop at different times. And again, this can improve nutrient utilization. So what is this plasma treated fertilizer that I mentioned? So this is a product which has been developed in Norway, and currently in the UK it's not commonly used. But the process is currently being looked into to see if it might become commercially available and to understand all the effects of using these treated products. So in the context of this experiment, we used pig slurry. So it starts off with that pig slurry being in a storage tank. The air within that storage tank is then ionized using electricity, and that forms a reactive nitrogen gas. This gas combines with the free ammonia that was already in the slurry to form ammonium nitrate, and it therefore increases the amount of inorganic nitrogen available for plant uptake that is within the slurry. So we are left with this product which is enriched in nitrogen and has a higher inorganic nitrogen content than untreated slurry. You can see the bullet point there at the bottom on the comment on the pH of slurry. So the process also reduces slurry pH, and that in turn can reduce methane emissions during storage, and it can also reduce ammonia emissions, which isn't a gas that I'm going to talk about today, but is also a considerable problem when we come to fertilizer application to land. So let's move on to the experimental design and see what we actually did. As I've mentioned, my PhD was conducted at the University of Leeds, which has a research farm. So we conducted this study there, and it was set out as a randomized block experiment. You can see there are chambers in the field, and they look slightly different to the picture on the title slide. And that's because at this stage in the crop's life cycle, we had applied those extensions to facilitate the crop as it grew taller over its life. And the crop in this study was winter wheat. So here we can see 6 chambers in the photo, but we did have 3 more which were a little bit closer to the camera. And this meant that we had 3 replicates of 3 different treatments. And these are listed on the slide there. So our first treatment was inorganic fertilizer, also known as a synthetic or chemical fertilizer. And we applied this in 3 different applications over the growth stage of the crop. In the instance of this study, we used this inorganic fertilizer treatment as a control because we wanted to simulate a practice that was typical of what would be used in the UK. Our second treatment was pig slurry and inorganic fertilizer combined, and when I move on to the plots later on, you might see this abbreviated as PS. So this treatment was 2 applications of untreated pig slurry, and then later on 2 applications of inorganic fertilizer. And again, that's often used where the organic fertilizer will be applied to the crop, and then later on in the growing season, we will top that up with inorganic fertilizer to make sure that the crop has had all of the nitrogen that it needs. And our third treatment, which will be referred to as TPS, was the treated pig slurry and inorganic fertilizer. So that was 2 applications of the plasma treated pig slurry, and then followed by those 2 top-up applications of inorganic fertilizer. And I mentioned the Eosense chambers in the picture there. We used these to measure carbon dioxide, methane, and nitrous oxide simultaneously and automatically. So as Nick and Karen have described, our Eosense chambers were linked up to the Picarro G2508 in the field, and this meant that every 2 hours we obtained a measurement of those 3 gases from each of our treatments, and this was automatically and continuously happening between March and June 2022. And this was brilliant because we could get emissions all throughout the day and night without having to go out and sample in the middle of the night, which was fantastic. So here's a quick snapshot of the environmental conditions during our study period, and the study period is the section that's highlighted there in the pink shading. So our top plot is PAR, or photosynthetically active radiation. The second one is the temperature, and then the bottom plot is the water-filled pore space in the rainfall. So that gives us an idea of how wet the soil would have been during our study. And if you're from the UK, if you're watching from the UK, you might remember that the summer of 2022 was particularly warm. We experienced drought conditions through a lot of the UK, and so our study site had very little rain and the soil moisture was very low, and it was also very hot. So that's important to bear in mind when we're interpreting our results. So first of all, before we jump into looking at the greenhouse gas emissions, we can have a quick look, first of all, at how the crop responded to those different fertilizer treatments. And I'm just flagging this as it's important to remember towards the very end of our presentation, so bear this in mind. And you can see here in the bullet point list, a list of all of the yield parameters and things related to the crop that we measured. We were interested in yield, the carbon and nitrogen content of the wheat, straw, but also the grains, the grain weight, and also the crude protein content of the grains. But as you can see, we didn't find any significant differences between any of these parameters for any of our treatments. So the crop responded and grew in the same way for all 3 of our fertilizer treatments, and we were given the same amount and volume of products for each one. So first of all, let's have a quick look at our carbon dioxide fluxes. And if any of you watching are familiar with greenhouse gas measurements, these might not look particularly exciting, but they might look quite familiar to you. So the top plot is showing the carbon dioxide emissions measured every 2 hours, and the bottom plot is showing the cumulative carbon dioxide over the measurement period. And our dotted lines there are marking the 4 fertilizer applications that we had. And you can see, which those experts amongst you might not be surprised by, that all of our CO2 fluxes were very similar for all of our treatments. And that relates to how the crop grew very similarly, photosynthesized very similarly for all of our treatments. And so nothing very surprising was happening there. However, when we come to look at the methane, it's a little bit of a different story. So again, here our top plot is the 2-hour fluxes, and then the bottom plot is our cumulative fluxes over the study period. And again, we've got those dotted lines. So our first 2 dotted lines are when the PS and the TPS had the organic treatments, and then the second 2 were when they were receiving the inorganic fertilizer. And so first of all, if we consider our inorganic fertilizer treatment, IF, which is the red line, you can see it's running all the way along the bottom of that top plot. And then hiding underneath that is also a blue line, which is representing our treated pig slurry treatment. So that means that we didn't have any methane emissions from the inorganic fertilizer treatment or the treated pig slurry treatment. And if we actually look at the bottom plot, the cumulative emissions there, you can see that for the red and the blue lines, it's actually decreasing very slightly. So for the inorganic fertilizer and the treated pig slurry treatments, we were actually observing a very slight uptake of methane over the study period, which does happen in agriculture, and that is common. So that was absolutely fine to see. However, the non-treated pig slurry, which is the green line, is a slightly different story. And you can see that on those first 2 applications which in this instance for the green line was the non-treated slurry, we had large peaks of methane emissions, and these then peaked and decreased on the very same day. So as I described earlier on, when we have untreated pig slurries in storage, the conditions are very suitable for methanogenesis, and that's what's happened here. When the pig slurry was being stored, the conditions were really, really great for methanogenesis and all those methanogenic bacteria, so they were producing methane. It was dissolving into our untreated pig slurry, and then that methane was released when it was applied to the field. So why do we have no methane emissions from the inorganic fertilizer treatment? Well, that's because it doesn't contain a carbon source for methanogenesis to occur. And why don't we have methane emissions from the treated pig slurry treatment? Well, that's because that drop in pH that is caused by the plasma treatment process was prohibiting that methane production because the conditions weren't suitable in the storage tank after that plasma treatment. And here we can just look at a few numbers for the methane to back up our plots. So when we think about the mean daily fluxes and the mean total fluxes, despite what we can see with those peaks in the data for the pig slurry treatment, we didn't actually find any significant differences between any of our treatments. And we think that this is because we did have a relatively small sample size for each of our treatments. However, if you look at the bottom row, this is focusing on the mean daily emissions taken between the first 7 days after those 2 fertilizer applications at the start. And you can see there the difference in the A's and the B's between the 3 treatments, and that's showing that we did find a significant difference. So when we're considering those first 7 days, that's where we find the exciting things are happening. So if we just have a quick zoom in on those first 7 days after the fertilizer applications, you can see that the 2 plots on the left have those peaks from the application of the untreated pig slurry. And again, that's due to that methane that was dissolved in the pig slurry being released. Whereas from our final 2 applications, when all of our treatments were receiving a chemical fertilizer, that methane production wasn't stimulated. Now we can move on to our nitrous oxide fluxes, and again the story is slightly different here. So as a quick reminder, we've got our red line, which is the inorganic fertilizer treatment, the green line, which is the non-treated pig slurry, and the blue line, which is the plasma-treated pig slurry. And immediately what you can notice are those really high peaks for those applications of the plasma-treated pig slurry. So these peaks occurred around 2 days after application, so there's a slight delay there, and then they declined back to a normal rate after around 7 days. And if we look at the second plot on the bottom there, those 2 peaks were making a really big difference to the cumulative emissions from the treated pig slurry. Looking at the other treatments, the inorganic fertilizer treatment, the red line, had a very small nitrous oxide emission, and the untreated pig slurry had a small emission of nitrous oxide because it does still contain a supply of available nitrogen. We can also have a think back to our weather plot. And as I mentioned, during the summer of 2022, it was very dry and very hot. So typically, when we have a very dry soil and it is wetted, whether that be water or a liquid slurry treatment, it stimulates nitrous oxide emissions. And so thinking about our 3 treatments, the treated and the non-treated pig slurry were very liquid, a volume of liquid was applied. And then when we think to our inorganic fertilizer, this was either granular or applied in a very small volume of liquid because that nitrogen was very concentrated. And so the more liquid that were in the organic treatments and the higher volume that was applied meant that they wetted up the soil more and further stimulated those nitrous oxide emissions. We can have a quick look at our stats again, and we can see here that our mean daily nitrous oxide emissions were slightly different between our 3 treatments, but the mean total emissions weren't. And again, we can attribute that to our small sample size. In addition, when we're considering the statistics, it's taking that mean daily emission, and we have a relatively small number of days where those emissions are elevated. However, and so the stats are kind of taking that information and thinking overall there's not too much difference. When we go back and consider the first 7 days after our fertilizer applications, similarly to the methane emissions, that's when we spot those significant differences, and all of our treatments were then significantly different from each other. So if we zoom in on those first 7 days, you can see those peaks in the data a little bit more clearly. you can see how the peaks from the plasma-treated slurry didn't occur until a couple of days after application, and how these remained elevated and decreased over the course of the week. So unlike the methane, where for the pig slurry treatment, it was immediately released from being dissolved in the slurry, for this treatment, it was more slowly released and didn't reach a maximum until 2 days after it was applied. On the second plot, you can also spot that green line there, and there's a slight elevation in emissions from the untreated pig slurry. Similarly, if we follow that green line across in our second plot, you can see that the emissions for the green pig slurry treatment actually start to increase and decrease, kind of like waves, and we can refer to these as diurnal nitrous oxide emissions. It was really exciting that we observed these diurnal nitrous oxide emissions, and you can see here over the course of the growing season that these were actually experienced by all of our treatments. So they would increase in the morning, peak in the middle of the day between around 10 and 2 o'clock, and then they would decrease over the afternoon and into the night. And it was great that we managed to capture these emissions using the automated chambers. If we were doing manual sampling, it would be really unlikely that we'd be able to capture these diurnal patterns, as there are huge logistics involved. We'd be having to go out in the middle of the night and in the middle of the day and several times over the course of the day, which isn't very appropriate when you have a limited PhD budget. And so using these automated chambers was great because we could capture those and the patterns were rolling over time. The evidence on the cause of these diurnal nitrous oxide emissions is mixed, and it's one of the emerging fields in nitrous oxide research. In 2021, research by Wu et al. They conducted a review, and for around half of the papers that they included in their review, diurnal nitrous oxide emissions were observed. However, for the other half of the papers, they didn't observe nitrous oxide emissions. And so the causes of this are relatively uncertain. We're not quite sure why they happen at the moment or what might cause them. However, researchers including Chadwick and Keane have suggested that higher temperatures, more photosynthetically active radiation, and potentially changes in soil moisture towards the middle of the day are simulating that microbial activity, reducing the oxygen availability in the soil, and therefore stimulating the denitrification and the nitrous oxide emissions. And so our data supports that. It wasn't a key focus of the study to identify those, but it's really great that we have this data and we can contribute this data to that knowledge pool, and maybe one day we'll discover what causes these nitrous oxide emissions. So next, our emissions have been converted to carbon dioxide equivalent, and this is when the non-CO2 greenhouse gases are converted to CO2 using their global warming potentials. So we multiply up methane and nitrous oxide by their global warming potentials to see what they look like on a CO2 equivalent basis. And although we didn't see that our numbers were statistically significantly different, we can see that numerically the emissions were lower from the inorganic fertilizer, about 34 grams of CO2 equivalent per meters squared. For the pig slurry, it was slightly higher, so this is the untreated pig slurry at about 89, and then they were considerably higher from that treated pig slurry at over 300 grams of CO2 equivalent per meters squared, and that's really attributed to that high nitrous oxide emission and the high global warming potential associated with that nitrous oxide. I previously said to bear in mind that our grain yields weren't significantly different between the treatments, and so this can be used to calculate and look into the greenhouse gas intensity. So this is the amount of carbon dioxide equivalent emissions per kilo of grain. And so our CO2 equivalent emissions were numerically different, but our grain wasn't. And so we found that this greenhouse gas intensity was much higher for the treated pig slurry, because a lot more greenhouse gases were emitted to produce the same amount of grain compared to the other two treatments. So to conclude, it's really clear that the greenhouse gas emissions are varying as a result of the fertilizer type that's used. We found that organic fertilizers, whether they were treated or untreated, tended to have higher carbon dioxide, methane, and nitrous oxide emissions upon application to the soil compared to that inorganic chemical fertilizer. We also found that when we were just focusing on that plasma-treated fertilizer, they had higher nitrous oxide emissions, but lower methane emissions compared to the untreated pig slurry. We also observed that the majority of the greenhouse gas emissions from organic fertilizers occurred within the first week, the first 7 days of their application. Compared to the other treatments, the nitrous oxide emissions were elevated for the treated pig slurry, and the methane emissions were elevated for the non-treated pig slurry. And as in any good scientific study, it's always important to consider where work could go with this in the future. In the context of this study, it would be really beneficial to consider a life cycle approach. So this would include looking at the emissions during the production and storage of the fertilizers, and also look at the emissions from transporting the products and from the machinery that is used to apply them to the field. We could also increase replication, do this over different types of crops or at different times of year as well, to see if there is any difference. So thank you very much for listening. I'd like to thank the many people on the screen who helped with the design and the delivery of the work, particularly on the days where it was very, very hot in the field, and also to the NERC Panorama DTP for funding the work. Thank you very much.
All right, superb stuff, Izzy, Nick, Karen. Let's just bring everyone back on stage and we can start the Q&A. So if you do have a question in front of our speakers, please just jot that in on the right-hand side of your screen. We've got about 15 minutes, 20 minutes or so. We'll try and get through as many as we can during that time. Izzy referenced the handouts. So if you look on the left-hand side of your screen, you'll be able to see the paper she was talking about, as well as various other handouts from Eosense and Picarro as well. So please do take a look at those before we finish up today. Izzy, I'll come to you for the first question. This one's asking, how was the plasma treatment conducted and how did this change the properties of the slurry?
Great, thank you. So the plasma treatment process is something that's quite new to the UK. It's used a little bit across Europe already, but it's still quite predominantly in its testing phase.
I think Izzy has just dropped off. So Nick, let me come to you for this question while we try and get her back up. So question 2 on the list, it says, how do you account for the volume of the stacking bases in your flux measurements?
Yeah, sure. So the stacking bases we have 2 different sizes, like I mentioned at the beginning. The Eosense software has a field where you can put an auxiliary volume in. So you just would put your auxiliary volume, depending on which base you're using in your experiment, into that field, and then the software will automatically recalculate the fluxes for that new volume. Alternatively, if you were varying them quite a bit during the experiment, you might also just do it kind of in post-processing, because it's a simple volume, additional volume calculation to the flux measurements, but the software definitely has that facility to do it as well.
Fantastic. And Izzy, I think we've got you back now.
Oh, sorry, did I disappear?
You disappeared whilst you were getting into the thick of your answer. So
where did I get up to?
Just at the start. So do you want to go with that one again? Oh. So how was the plasma treatment conducted and how did it change the properties of the slurry? Although the world doesn't want you to answer this question tonight, so.
Can you hear me?
Yeah, so what we're going to do is we're just going to turn off your webcam and see if that takes away some of your bandwidth, and we might be able to work with you better. Whilst we're doing that, Karen, I'm going to come to you for a question, if that's okay. This one's asking, is the new Sage auto sampler compatible with all the Picarro analyzers, or are there specific models it works best with?
Yeah, so the Sage autosampler is compatible with most Picarro autosampler. We do have a special autosampler for the liquid or for ISO water analyzer, so it has its own autosampler, but the rest of them are compatible. It is working, for example, with the 2508, and we did use it and to generate a lot of data. And yeah, thank you.
Superb. We will try and get Izzy back because a lot of the questions are aimed at her, so we will do our best to get her back up and running. If for any reason we can't, we'll obviously forward all the questions onto her and get her to come back to you via email. Nick, how about I come to you for this one? How long do chambers need to be closed to make an accurate flux measurement for nitrous oxide?
Yeah, that's a good question for this in particular. So I mean, Izzy can maybe tell us a little bit about how long she closed her chambers, but we typically see between 10 and 15 minutes with the large chambers to make a good nitrous oxide flux measurement. If the volume is on the lower side, you might be able to get away with a 5-minute closure. If the volume is on the higher side with the big stacking bases, something like 15 or 20 minutes is better. But you can, the good thing about the Picarro is you can kind of watch in real time the fluxes for a few measurements and kind of judge where you feel comfortable setting your closure time so that you get enough increase over that kind of closure time to feel confident in your flux measurements, if that makes sense.
All right. Izzy, I know you've tried again, so we're going to try one more question for you with your webcam off now. Let's see if that makes any difference. Let's go with this one. Michael's asking, how many chambers per treatment replicate?
We had 3 different treatments, and then we had 1 plot per treatment replicated in 3. So we had 9 different plots with 1 chamber on each of them. So we had 3 by 3 essentially.
Fantastic. And whilst we've still got you, I'm going to just try and get through a few questions in case we lose you again. Number 12 on the list is asking, perhaps you mentioned it and missed it, but were nitrogen application rates the same for each treatment? And if so, does that mean the TPS or the pig slurry was applied at a lower rate than the other pig slurry? That's
Am I there?
question.
Can you hear me?
Yeah, we're just going through question 12, Izzy.
Let me find it. Anytime I speak, it seems to go off. Question 12. Yes, so we aimed to apply them all at the same rates. We did some slurry analysis slightly after due to timing, and so the treated pig slurry had a very slightly higher nitrogen content than the untreated pig slurry. So that meant it was applied at a slightly higher rate, but the difference was very, very small. So it was unlikely that difference is what caused the difference. But yes, it would have been good if we'd managed to get in some nutrient analysis before we'd applied, but we didn't have time, unfortunately.
And how about we take question 13 as well? Did the methane emission follow the same pattern each time you applied pig slurry? It's a moment of anticipation every time we put a question to Izzy to see if we've still got her. We will come back to that if she can come back on the line. Let's have a look at, let's go with question number 9 on the list. Karen, this is a question about the Picarro G2508. Can it be used with multiple chambers in the same experiment to measure soil flux across the different setups?
Yeah, so I think the answer is yes. There is, you can connect to a multiplexer, and basically that will connect multiple chambers to the analyzer, and it will rotate between them for the measurement. Nick, I don't know if you have anything else to add on this.
Yeah, I mean, that's the basic idea. We have a 16-port multiplexer from Eosense that will allow you to do, I think Izzy had the 12-port, one of our older systems, but we have a 16-port that will allow you to do up to 16 chambers in recirculating mode. You can use big chambers, small chambers, transparent chambers, light chambers. So you can kind of, make your experiment the way you want it with those kind of selections.
Perfect. And then Nick, if I come to you for question 7, I don't think we've tackled this one yet. Can the chambers measure ammonia fluxes as well?
Yeah, and I noticed that was also somebody else's question, number 18. I think Izzy might also be able to add to this if she can pop back on, but the ammonia fluxes are tricky. Like we just kind of went through this internally because ammonia is such a polar molecule, and it's so it interacts with all the surfaces, and it interacts with water. It is really tricky to measure. You can do it, but you need to do a lot of modification to the chamber. So this is post-sale modification to the chamber, like coating surfaces in Teflon or PFA, doing things like replacing fittings and heating lines and increasing flow rates. So the short answer is not off the shelf. You cannot, but if you do some modifications, you can get it to do a better job of measuring ammonia emissions. And this is something we're actively looking into too, is how do we make it better at doing that? Because we know a lot of people want to monitor ammonia.
All right. Izzy, right. We've got a question. Let's try question 20.
Let's have a look.
This one's asking, did you use mainly the exponential or the linear approach to obtaining the slope for the flux calculation for the 3 gases?
We used the linear approach, so we based this on the carbon dioxide fluxes and then kind of applied that to the associated measurements of the other gases, which we were able to do in the eosAnalyze software. So yeah, we went with the linear approach this time.
Wonderful. And I'm going to come back to question 13 because you were midway through the answer. This one's asking, did the methane emission follow the same pattern each time you applied pig slurry?
Yes, it did. So the untreated pig slurry, as soon as we applied, the methane emissions immediately shot up, and then they were kind of back to normal within 24 hours. And that was for the 2 applications of the untreated slurry. And yeah, for the treated pig slurry didn't get any, but the untreated they followed the same pattern.
Perfect. And we're going to go again. So this one's asking, number 8, is the plasma technology used widely across the agricultural sector for treating slurries?
Not currently. It's not widely used. It's not commercially available at the moment. It is used in select farms in Norway and Denmark. But at the moment, for use in the UK, for example, it's currently kind of still undergoing a lot of testing, similar to what we've done to kind of see what the effects are, because there's a lot of things to consider. So we might see it in the future, but at the moment, it's not on the market. It's not used very widely.
Perfect. There's a couple more questions. Well, there's plenty of questions for you. I don't know if you want to have a quick look through them to see if you want to prioritize any of them. Just whilst this is doing that, just a reminder that there are several handouts on the left-hand side of your screen that you can download before we leave the webinar today. So please do take a look at those and download them. There will be a feedback form that appears on your screen once we finish as well. So please do give us your feedback there. And a reminder that we will be sending out a recording within the next 24 hours. So if you have missed anything, you can watch back anything that you haven't caught today. Okay.
Did you hear me when I talked about the application rates, or did we not quite catch that?
Would this be, which question was that?
That was question number 12. I think we got that one.
Yeah, I think we got that one in.
Quick look now. Yeah, number 21 is an interesting question. With agriculture contributing a large proportion of nitrous oxide and methane, at which stage in the value chain are the gases released most? That's a really interesting question, and I think there are so many different stages of the chain where it happens. I know a lot of these emissions come from organic waste storage and application. That's a really, really huge one, but also particularly ammonia and methane we get from like housed livestock. So that's a really big source as well. And yeah, similarly with carbon dioxide as well, which wasn't really touched on in this, but when we're using inorganic fertilizer, there's a whole host of emissions with transporting the fertilizers and the tractor on the field, applying the fertilizers. So I think that's a really interesting question, and I might think about it a bit more and reply in a bit more detail, because that's got me thinking. I'm just looking at number 22. We had the Picarro tied up for several months at one site. I'm just looking at Chris Curtis's question.
Yeah, go on, Izzy, go ahead.
No, I'm just thinking, I think we got some really interesting results from having the analyzer there for the entire length of time, and especially with the diurnal nitrous oxide fluxes, for example, the way that the three treatments aligned with each other in that kind of bell curve really became much more apparent towards the end of our study, when all the fertilizer had kind of been utilized. And I think if we'd kind of stopped early, or if we hadn't measured towards the end or nearer the start of those diurnal fluxes, we wouldn't have seen how they aligned more with each other over time. So I think the fact that we kept it going for so long was a good thing. I don't think we would have got the same quality of results if we had done it periodically for weeks, for example, just because nitrous oxide and methane are so variable and they can be affected by anything. And also the interactions with the weather. We don't quite know what's going to happen. So any kind of surprise rainfall events or really hot days, we were able to capture those as well. So yeah, I would advocate for long sampling times.
Yeah, still can't quite believe it was a drought in the UK over the course of this experiment, but
yeah, I didn't expect to be in the field in my sun hat and my shorts, but I was.
Wonderful. I think we'll quit while we're ahead, Izzy. But as a reminder, if your question hasn't been answered, we'll forward all the questions onto the speakers. We'll get some replies via email and some more details to the question that have been answered already over the next couple of days or so. So if your question hasn't been answered, do bear with us. We'll get to you as quickly as we can. Final reminders that you'll get a link to the recording in the next 24 hours. So please do look out for that in your inbox. Share it internally with anyone else in your teams you think would benefit from seeing the webinar as well. And of course, you watch back anything that you missed on demand. Any final thoughts from anyone? Izzy, I'll come to you first before we wrap things up.
Final thoughts. I just think it's really exciting to be able to do this kind of research and be able to kind of get continuous fluxes, which we haven't really been able to historically. So yeah, I'm excited to see what happens in the future.
Perfect. Karen, I'm just going left to right across my screen now.
Yeah, no problem. I want to say big thank you, Izzy. This was very interesting work you've done, and I really enjoyed it. Thank you.
And Nick, last but by no means least, have you got anything to add?
Yeah, I just echo Karen's comments there and thank everybody for attending.
Perfect. Yeah, big thank you to everyone for tuning in from across the world. Big thank you to the three of you for joining us and presenting, sharing your expertise. Izzy, thanks for bearing with us, and we got you there in the end, and we've got through most of the questions. So thank you very much. We'll finish things up there. Big thank you again to everyone in the audience for joining us from across the world. We wish you a pleasant rest of the day and hopefully see you all again very soon. Take care.